Thank you. Can you hear me? Okay. Okay. Good morning, everyone. I would like to thank to the organizer for this opportunity to talk about the work we are developing in Mexico. So I'm Ricardo López. I'm a postdoctoral fellow at Star Forming Group. We are working in the Star Forming Group Institute of Astronomy in UNAM and in Ensenada in Mexico. And this is the list of my main collaborator of this work. So we are trying there to do an homogeneous characterization. Means homogeneous characterization means atmospheric parameters and chemical abundances, just to try to characterize pre-main sequence. So this first part of the work is just try to test this methodology on a main sequence stars. So as we already know, today we have large stellar samples. We have a lot of stellar spectra at different wavelengths, different resolution. And of course, we have different population. We have giants, we have main sequence stars, we have pre-main sequence stars. So characterize the samples is really complicated within the survey because these things. So if you are the survey, you try to solve this, developing a pipeline that work on average well for all the population. But if you are trying to characterize a specific population, you will find some issues. So often this kind of characterization relies on a comparison between theory and observations. When you compare stars that are in common in different groups, you will find difference between the parameters. That is that complicated if you want to collect and to make an homogeneous sample. And these differences sometimes are larger than the typical errors on the parameter. So there's a complication and you need to take into account. And I will just try to skip that part. I will talk more about that. So recently, as we see, so the field is moving just to try to apply data-driven techniques, which of course in this approach, you also need a training set. So this training set needs to be a large sample or an homogeneous determinant. So an homogeneous determination as we want to do it, so it will be helpful in this sense too. So the talk is based on a work that is under review right now. So we present, characterize, and test a methodology that we want to apply to pre-main sequence stars. So that's the main idea. So the homogeneous characterization includes parameters and chemical abundances. And we are looking to try to at least have the same performance than previous published values. So we are using apogee data. As the UNAM, we are a member of the SDSS collaboration, so we have access to apogee data. The apogee spectrograph is a high resolution infrared spectrograph. So we construct our sample just doing a cut in distance. So we are just focusing on stars within 100 parsecs, and we are just trying to reduce the contamination by binaries with these Gaia-Ruhe parameters. We just remove a star with circumstellar extinction, and we focus on the main sequence through photometric diagrams. Our final sample comprise over 1,600 main sequence stars that likely belong to the thin disk. So the atmospheric parameters. We are using in Ensenada, we are using an heuristic multidimensional code that is based on a sexual generic algorithm that is developed by another postdoc, Lucia Adame, and we call it Tonali. So this Tonali code was developed to work with apogee data and also with different theoretical grids. In short, just Tonali is just doing a chi-square minimization between theory and the apogee of spectra. We are our synthetic spectra is based on Mark's atmosphere, Mark's models. And the new thing or the approach that we are taking is we are using 2-mass and Gaia photometry together with parsec colibri isochrones to construct a prior on surface gravity. In this way, we are obtaining better atmospheric parameters, you will see. And Tonali is just the output of Tonali is atmospheric parameters, so temperature, gravity, metallicity, alpha element Haussmann, and the rotational velocities. So this is an example. This is the apogee spectra, 3 different chips. And you see in green is the observed spectra for this random star that I took it from a sample. And in blue, you are seeing the tonality best fit. And you see how rich is the apogee spectra, all the lines that we can use. They're really nice data. And these are our results for this part. Well, I don't have time to show all the parameters, so I just focus on temperature and gravity, which are the more complicated gravity instead. So this is the kill diagram, temperature against gravity for our sample, and you see in green our results, and the color lines are the isochrones for these ages and metallicity. And you see our sample is behaving good in this diagram. So this maybe for you say, oh, it's fine. But the thing is it's complicated to get this. I'm showing this. This is the results that we have in the apogee pylon. Apogee pylon is producing this flat main sequence for this sample. So you can see that it's not easy to get the result that we have with tonality. Of course, with an apogee, we know this issue, and we apply a calibration to the gravity, and it improves a little bit here. So we compare our parameter with the apogee data, data release 16 and 17 with the calibrated estimation. So we are in agreement with the calibrated estimation without applying any calibration ourselves. So we also compare our results or parameter with Gaia and Apogee Net. Apogee Net 3 is an effort to re-characterize the Apogee data, doing a better job than the pylon, the original pylon. And we see here we create an alternative color temperature relation to 2 mass and Gaia colors. In gray, you see our results. The red crosses are just our results, median colors in temperature bins. And you see here in this panel, in the sign line is the Gaia color temperature, and we are seeing that we have good agreement with that. Now we have the parameter where the next move is just try to compute chemical abundances. Chemical abundances are important in various astrophysical fields, some of them the formation and chemical evolution of the galaxy. To do this, we are employing Bacchus, which is basically computes and compares synthetic spectra against observation on a line-by-line basis. We have all the requirements to run Bacchus. We have a set of atmospheric parameters. We set model atmospheres. We have observation, again, the apogee data. And we are using 35 lines of these 5 elements to determine the abundances. So this is an example how Bacchus works. So you see here, the black line is the observed spectra in this certain iron line, and the different color lines and different models with different iron abundances. So basically, Bacchus is just trying to find the best fit, moving this abundance through 4 different methods, and also assigned a flag quality for every fit, just to let you know if the fit is good or not. We apply our techniques to the sun. We have in Apogee the best asteroid spectra, so we can apply and obtain our own solar abundances. And you see here the results. Our scale or solar abundance are really similar, pretty similar, very, very similar to previous determination, which is good. It's one of the goals of the project. Try to reproduce, or at least try to have consistent results. Let me just pass this. Okay, this is what I want to show. So in general, our results for all the elements, we found abundances, the mean abundances that are subsolar. So meaning in this bracket notation that we have negative abundances in all the elements, slightly negative. This is in agreement with the studies for the solar neighborhood in J and K stars, which is good. Again, we are obtaining abundances that are really in accordance with the previous publication. For the cool stars, we have systematic lower abundances in all the elements. So our abundances in the cool stars are more negative than in the hotter stars. So it's something that we are just trying to figure out what's going on. We think that it could be a problem in the model atmosphere, but we are still working on that. And here in this plot, I am showing the comparison. This is a delta abundance. It's a difference between the apogee and or abundances as a function of the temperature and the metallicity or determination. And you see basically in all the elements that the difference are around zero. The crosses, the green crosses or the data, and the black crosses are the median difference in beam of temperature. So what's next? So as I said in the beginning, our goal is just try to apply this to the premise sequence stars. So that's the real goal of all of this. But we needed to be sure that we are doing a good job. So these are preliminary results for this in this sense. So we apply all our techniques to more than 600 joint stellar objects located in Orion in these 4 different groups. So and here I show you, we have parameters, the atmospheric parameters for these YSOs. We have these abundances for these 5 elements. And I'm showing you here just the box plot of these iron abundances in these different groups of Orion. So there is an open debate about if the Orion is homogeneously or inhomogeneously chemically speaking. So we can see here our results seems to find there's hint that or at least with these members, we're finding that the Orion complex is homogeneous. And this behavior is repeating in all the elements. So you also see that our median values are still negative, so solar values, which is something in agreement with previous publication. So my conclusion here, so we are obtaining really good parameters, atmospheric parameters, applying this new technology, this code tonally. It's a different approach. With these parameters, we are producing also, these parameters in some cases are superior to previous ones. And with these parameters, we are producing good abundances, chemical abundances, at least for J and K stars. So thank you very much.
Before we get to questions, thank you to the suggestion on Slack. Please introduce yourself when you're asking a question. Your hands up, please.
Hi, I'm Zach Wade from Georgia State. I have a simple question as last time. So with a GUI cut, you have a lot of latent equal mass binaries left over in the sample. I was wondering if you thought about any of the biases that might introduce into spectrum.
Yeah, that's a good question. We try to remove it with the Gaia-Rue parameter. So I know that maybe there may be some remaining of binaries. So right now we are not taking care of that, but it's a good point to take in mind. Thank you.
Hola, Ricardo.
¿Qué tal?
Nice to
Thank you.
Toda la investigación de la Universidad de Tarapacá. I was wondering what you were saying about the results that you got for Edwards, that you were getting lower abundances than what you would expect in the UK stars. My question is related to the normalization that you're using for the spectrum. Are you using something different for Edwards, or are you basically normalizing everything to one?
Yeah, it's the same. It's the same methodology for J, for all the sample. So the problem with the MDORs, so in some cases, we have, for example, a small number of lines for each element. So for example, in magnesium, we had 3 lines. We're using 3 lines. So in these cool stars, sometimes you have lenders, you have issues with the reductions that you lost some lines. And at the end, you had just 1 line. So the thing is, in the other stars that you have a good fitting, by eye and visual inspection that I'm doing, you see that it's a good fit. So, and that's the weird thing. When we have a good fit in the lines, you have a good or a decent normalization, you also are getting these lower values. So my guess is that is the model, I'm not sure.
Thank the speaker one more time. Thank you.
Yeah.